course, Lesson 3, Factored Form Polynomial Functions. In this section, we're going to be looking at the relationship between a factored form equation of a polynomial function and the x-intercepts of its corresponding graph. And we're also going to look at how the order of the factors in the factored form equation can affect the shape of the graph at the x-intercepts. So let's do this investigation together. If we want to graph this polynomial function here that I'm giving you in standard form, it would be most useful to look at the factored form version of the function. And you see that below. I've got it in factored form for you. Now, we don't know yet how to transition from standard form polynomial functions to factored form. We'll learn that next unit. What we're going to be focusing on this unit is how this factored form version of the polynomial function helps us be able to sketch the graph of the function accurately. So I've given you three versions of the function here. Standard form equation, factored form equation, and its graphical representation. Let's answer some questions using those pieces of information. Part A says, what's the degree of the function? That's most easily found from the standard form version. We just look at the highest degree term in the standard form version of a polynomial function. The highest degree term is the x to the 4 term. Therefore, the degree of the polynomial function is 4. Part B says, what is the sign of the leading coefficient? Well, what's the leading coefficient of that x to the 4 term? Well, we don't see it, but it's there. It's a 1, and that's positive. So the leading coefficient is 1, so therefore the leading coefficient is positive. Here's what we want to focus on. Part C, what are the x-intercepts? Now, from the standard form version of the equation, we wouldn't be able to easily tell the x-intercepts. I wouldn't be able to easily tell what would make this equation be 0. Remember, at an x-intercept, the y value is 0, so if we can figure out what value of x makes the equation be 0, we know the x-intercepts. I can't tell that from the standard form version. I mean, I could start guessing and checking, and I might find something. But it's very easy to tell what would make this factored form version equation become 0. Because do you remember the zero product rule? The zero product rule tells us that the product of a set of factors equals 0 if any of the factors are 0. So if this factor was 0, the whole product would be 0. If this factor was 0, the whole product would be 0. Or if this factor was 0, the whole product would be 0. And what numbers make those factors be 0? -1 would make this factor become 0. -2 would make that factor be 0. And 1 would make that factor be 0. That's why down here we see x-intercepts at -2, -1, and 1. So what are the x-intercepts? They were -2, -1, and 1. And you're going to see some other information here about orders of x-intercepts. And you could probably figure out where I'm getting that information from, but we'll more clearly define what the order of an x-intercept is in just a minute on the next page. For now, simply put, notice that at -1, I said the x-intercept is order 2. If we look back to the factored form equation, -1 is what makes this factor become 0. And notice what's the exponent on that factor? 2. We can tell the order of the x-intercept based on the exponent that is on the factor that creates that x-intercept. And that's going to be important because that's going to tell us what shape the function is going to take at the x-intercept. And we'll look at that more closely on the next page. What's the y-intercept? Actually, the y-intercept is probably easiest to find from the standard form version of the equation. If we look at the standard form version of the equation, well, at the y-intercept, I know the x value is 0. So if I plugged in 0 for all the x's, all of these terms would be gone, and we'd be left with just -2. So the y-intercept would be -2. In a standard form version of a polynomial function, the constant term tells us the y-intercept. Notice on the graph, here's the y-intercept, -2. We could also plug 0 in for these x's and find the y-intercept, but if we have the standard form version, we just look at the constant term. So the y-intercept is the point 0, -2. Now I want to look at what happens around the x-intercepts that we found, the x-intercepts of -2, -1, and 1. So what we're going to do is we are going to divide the graph up into 4 sections using those x-intercepts as dividing points. So let me go back to this graph and let me draw some vertical lines through the x-intercepts. So notice I now have 4 sections. 1, 2, 3, 4. I have 4 sections of the graph. Part E wants us to complete this table. It says the x-intercepts divide the graph into 4 intervals. Write the intervals in the first row of the table. In the second row, choose a test point within the interval. And in the third row, comment on the sign of the function. And we don't actually need the test point. If we have the graph, we can just look at the graph and see if the function is positive or negative. But I can just show you how we could use a test point if we didn't have the graph of the function. So the intervals of x values. We're going to describe the interval of x values in section 1. So that'll be all x values from negative infinity all the way to negative 2. So I'll write it in bracket notation from negative infinity to negative 2. The next interval would be from here to here, from negative 2 to negative 1. In bracket notation, that looks like this, from negative 2 to negative 1. Interval 3 would be from negative 1 to 1. And interval 4 would be 1 to infinity. And as we fill in the rest of this, I'm going to refer to this graph in Desmos to help us calculate these values. Okay, so I have Desmos with the graph of that function, and I have this point that I can drag along the function, and it will tell me the x and y coordinate of the point. We could also look over here if we wanted to see the y coordinate of any point for the given x value. So I want to, within the first interval, from x values between negative infinity and negative 2, I want to pick a test point in that interval, so any x value between negative infinity and negative 2, so how about negative 3? And this function was called f at x, I believe, so let's figure out what is f at negative 3. And we would plug it into the original equation, either standard form or factored form. I'm just going to get Desmos to calculate it for me. When x is negative 3, it tells me the y value is 16. It's way up above where we can see. I won't scroll all the way up there. X value of negative 3 is 16. That's positive, so that tells me that the function within that interval is positive. And we can clearly see that from the graph. Before an x value of negative 2, the function is above the x-axis, therefore positive. In this section, it's positive. How about between negative 2 and negative 1? We need a test value in that interval. So how about negative 1.5 can be our test value. And there's the y value, negative 0.3125. So the function is negative in that interval. And we can tell that from the graph because in that interval, the function is clearly below the x-axis. Between negative 1 and 1, we need a test value. How about 0? And the y value for an x value of 0 is negative 2. So f at 0 equals negative 2, and that is in fact the y-intercept. We already knew that. So the function is negative in that section. And in the final section, between x values of 1 and infinity, we need a test point. So how about an x value of 2? And let's test that in the function. An x value of 2, we won't be able to see on the graph. It's way high up there, but the y value is 36, which is positive. And yes, the graph is above the x-axis there. That's why it's positive. So we didn't need those test points if we see the graph, but if we didn't have the graph, we could just plug those test points into the standard form or factored form version of the function and get the corresponding y values and then comment on the sign of the function. The reason why I had you do this is because I wanted you to look carefully at when does the function change sign and when does it not. The function changed from being positive to negative at the x-intercept of negative 2. And let me just label these dividing points here. The x-intercept was negative 2. Here is the x-intercept of negative 1. And here is the x-intercept of 1. So at the x-intercept of negative 2, the function switched signs. At the x-intercept of 1, the function also switched signs. It switched from negative to positive. But at the x-intercept of negative 1, the function did not switch signs. And if we look at the graph, at the x-intercept of negative 1, let me zoom in a little bit, the function just kind of bounces off the x-axis. It doesn't actually cross. At negative 2, it crosses straight through, and at 1, it crosses straight through. But at negative 1, it just bounces off. And the reason why it does that, well, look at the factor that creates the x-intercept of negative 1. There it is there, x plus 1 squared. It has an exponent of 2 on it. So what happens at the x-intercept of negative 1? It looks like a degree 2 power function. It looks like a parabola. It just bounces off. What happens at the x-intercept depends completely on what the exponent on the factor is that creates that x-intercept. And we call that exponent the order of the x-intercept. So let's jot down what happens. At negative 2, 0, which was order 1, the exponent on the x plus 2 factor was 1, the function changed signs. At the x-intercept of -1, 0, which is order 2, the function did not change signs. And at 1, 0, which was order 1, it changes signs. And in fact, a short rule we could know here, if the order is even, the function will not change signs. If the order is odd, the function will change signs. So let's write down some conclusions about what we just discovered in this investigation. So the x-intercepts of the graph of the function correspond to the zeros of the corresponding equation. We know that from previous math courses. For example, this function here, this f of x equals x minus 2 times x plus 1, its x-intercepts are the x values that make this product become 0. So what makes this product become 0? Well, if we could find an x value that makes this become 0, so 2, or this becomes 0, so -1, it would make the whole product be 0, making the y value become 0, meaning it's an x-intercept. So 2 and -1 make that product become 0, meaning they're x-intercepts. They're the roots or the zeros of the equation. They're what make the equation become 0. The next thing we need to talk about, and I've said it a bunch of times, is about the order of a factor. So if a polynomial function has this factor x minus a, which is some number, that's repeated n times, meaning there's an exponent n on it, that exponent n is what we call the order of the x-intercept that is at x equals a. So another way of saying it, order is the exponent to which each factor in an algebraic expression is raised. So for example, let's look down here at this factored form polynomial function, x minus 3 squared times x minus 1. There are two x-intercepts, there are two x values that make that product become 0. 3 would make that factor be 0, and 1 would make that factor be 0. So those are both zeros of the polynomial function, meaning they're both x-intercepts. But this factor has an exponent of 2 on it, meaning the x-intercept of 3 is order 2. So it has a 0 of order 2 at x equals 3, and a 0 of order blank at x equals 1. Well, this factor, if x was 1, would become 0, and what's the exponent on that one? 1. So it's order 1 at the x-intercept of 1. And we talked about this already as well. The graph of polynomial functions change signs at zeros of odd order, but do not change signs at zeros of even order. And let's look at the shapes that happen based on the order of the x-intercept. Okay, let's just have a look at this function I'm giving you here, this f of x function that is in factored form. It has 3 x-intercepts. We can see them clearly at -2, 1, and 4. What I want you to pay attention to are the 3 different shapes it makes at those x-intercepts and how those shapes correspond to the order of the x-intercept based on the exponent that is on the factor that created that x-intercept. So this x-intercept at -2. That x-intercept is order 2. I know that because that x-intercept comes from this factor, and that factor has an exponent of 2 on it. Notice the function doesn't change signs there, and notice the shape. It looks like a parabola. What does a degree 2 power function look like? What does x squared look like? It looks like a parabola. Okay, how about at this x-intercept 1, 0? Well, what factor does that come from? It comes from this factor. And what exponent is on that factor? 1. So we say this x-intercept is order 1. And what shape does it look like it takes through that x-intercept? It goes straight through it. It looks like a degree 1 power function. What does x to the 1 look like? It looks like a straight line. And lastly, the x-intercept at 4, 0. That x-intercept is order 3. I know that because if I look at the factor that created that x-intercept right here, the exponent on that factor is 3. It makes this kind of S shape through that x-intercept. Why does it make that S shape? Well, this is order 3, and what does a degree 3 power function look like? It looks like that. And if we had an order 4, it would look like a degree 4 power function. It would look like the parabola, just a little flatter, and so on. Let me just show that to you in Desmos, how changing the exponent on the factor affects the shape of what happens at the x-intercept. Okay, here's that same function. I have it being graphed in green and red right on top of each other. Just so you can see what happens if I change the order of the x-intercept by changing the exponent on the factor. So for example, let's pay attention to this one at -2, the x-intercept at -2. Right now, it looks like this parabola shape. It just bounces off the x-axis. If I changed it to order 1, watch what would happen at that x-intercept. It would just go straight through. See, it just goes straight through. If I changed it to 3, it would make the S shape. But it was 2, so it makes the parabola shape. If it was 4, it would still make that parabola shape, but be a little flatter. If it was 6, same thing, but even a little flatter. 8, same thing, but even a little flatter. You wouldn't be able to tell the difference, let's say, between like an order 4 and order 6 x-intercept. You could guess, but I'll just tell you, when I'm giving you questions, I'll only give you order 1, 2, or 3. So you should clearly be able to tell the difference between order 1, 2, or 3 at an x-intercept, whether it looks like a degree 1, 2, or 3 power function. Okay, let's go through 3 examples helping you solidify your understanding of orders of x-intercepts and how that affects the shape of the graph at the x-intercepts. So example 1, I'm going to give you the graph of a polynomial function, and you're going to tell me 3 things: least possible degree and the sign of the leading coefficient. We learned about that stuff in the first couple lessons of this unit, so it's a good throwback to that. Part 2 says what are the x-intercepts and the factors of the function. And part 3 says the intervals where the function is positive or negative. So part 2 and 3 are the new stuff for today. Let's do part 1 first for this function. So when we're finding the least possible degree, you have to remember a couple of things from the first 2 units. You have to remember a degree n function at most can have n x-intercepts, and at most n minus 1 turning points. So for example, a degree 10 function could have at most 10 x-intercepts and at most 9 turning points. So if we're finding least possible degree, well, we're able to see the x-intercepts and turning points. We have to think backwards a little bit. To find the least possible degree from a graph, we're going to be analyzing 2 things. The least possible degree, it has to be at least equal to the sum of the orders of the x-intercepts. So let's make a note here. So least possible degree, we're going to check 2 things. At least equal to the sum of the orders of the x-intercepts. Second thing, it has to be at least 1 more than number of turning points. And as we go through these examples, I'll explain to you why these actually make sense. Or like, for example, if we had a function that had 7 turning points, well, that can't be a degree 7 function. A degree 7 function could have at most 6 turning points, so the function would have to be at least degree 8. But I'll talk to you about this as we go through as well. So example 1, I see 3 x-intercepts. 1, 2, 3. It might actually be easier if we answer part 2 first and then go back and answer part 1. So there are 3 x-intercepts. The x-intercepts are at -5, 0, and 3. So let me write down the x-intercepts. The x-intercepts are at -5, 0, and 3. Now what factors would create these x-intercepts? So we have to think, okay, we had some factor that when we set it to 0 and solved, we got -5. Well, what factor would create that x-intercept? We have to reset it back to 0. Move that -5 over, we'd get x plus 5 equals 0. Okay, well the factor of x plus 5 would be the factor that would create the x-intercept of -5. So hopefully you could follow that logic there. So I'm going to list my factors. X plus 5 is one of the factors, right? That factor set to 0 and solved would give me -5. -5 is the x value that makes that be 0. What factor would give me an x-intercept of 0? Well, what factor set to 0 becomes 0? Just x. And what factor set to 0 gives me 3? X minus 3. Those are the factors. And notice on all 3 of those factors, there's just an exponent of 1. I know that because if I look at all 3 x-intercepts, it goes straight through all 3 of those x-intercepts. Therefore, they're all order 1. So if I add those orders together, that would give me one of my 2 checks for finding least possible degree. So it's at least equal to the sum of the orders. So 1 plus 1 plus 1 is 3, so it has to be at least degree 3 according to that. But we also have to check turning points. Has to be at least 1 more the number of turning points. there are 1, 2 turning points, at least one more than that. So yes, it is degree 3. So least possible degree equals 3. And why are we saying least possible? Well, for all we know, it does up here outside the graph that we can see, there's 2 more turning points, which mean it has to be degree 5. But based on what we can see, it has to be at least degree 3. What's the sign of the leading coefficient? Well, since it goes from quadrant 2 to 4, we know an odd degree function, for it to go from 2 to 4, would have to have a negative leading coefficient. And now let's talk about the intervals. And the x-intercepts are the dividing points of the intervals. So the x-intercepts are -5, 0, and 3. So I'll just put -5, 0, and 3. And those are my dividing points. So the interval before -5, I'd write from -infinity to -5. And then from -5 to 0. And then from 0 to 3. And then from 3 to infinity. And now what's the sign of the function in each of those intervals? So from -infinity to -5. So that means over here, where's the function? It's above the x-axis. It's up here. It's positive. How about from -5 to 0? Well, the function is down here. It's below the x-axis. So it's negative. From 0 to 3. So here, the function's above the x-axis. So positive. And from 3 to infinity, below the x-axis, negative. Notice it changes signs at all 3 of the x-intercepts. That's because all 3 of the x-intercepts are odd order. They're all order 1. Let's try another one, part B. Let's start with the x-intercepts again. The x-intercepts are -2, 1, and 3. So x-intercepts. What factors create those x-intercepts? So once again, I'm trying to figure out what factor would give me the x-intercept of -2. Reset it back to 0, move that over, and I get x plus 2 is the factor that when set to 0 and solved, we get -2. So x plus 2 is a factor. X minus 1 is a factor, because an x value of 1 plugged into that factor would make it become 0. Therefore, that gives me the x-intercept of 1, 0. And lastly, the factor that would create the x-intercept of 3 would be x minus 3. Now, I need to be careful with what exponent I put on each of those factors. At -2, it goes straight through, so yes, that is order 1. At 1, it goes straight through, so yes, that is order 1 as well. But at 3, it looks like it just bounces off like a parabola. It looks like a degree 2 power function at that x-intercept. So that means that factor must have had an exponent of 2 on it. That x-intercept is order 2. So when I'm doing least possible degree, it has to be at least equal to the sum of the orders on the x-intercepts. So the sum of the orders is equal to the sum of the exponents on the factors. So 1 plus 1 plus 2 is 4. So least possible degree, we would say 4, but we should also check and make sure it's at least 1 more than the number of turning points. How many turning points are there? There are 1, 2, 3. It's at least 1 more than that. So yeah, at least 4. And let me do the intervals quick. So my x-intercepts were -2, 1, and 3. So let me define the intervals of x values around those x-intercepts. So from -infinity to -2, from -2 to 1, from 1 to 3, and then from 3 to infinity. So the function before an x value of -2 is up here. It's positive. After an x value of -2, but before 1, so between -2 and 1, it's down below the x-axis, negative. Between 1 and 3, the function's positive. And then from 3 to infinity, the function is still positive. For both of those examples, when we checked both of these two things for least possible degree, we got the same answer. But that's not always going to be the case. Let me just give you a quick example of what I mean. Okay, this function, how many turning points does it have? Just 1. So if we were to follow our rules, it says it has to be at least 1 more than number of turning points. You would say least possible degree is 2. But in fact, that's wrong. I know this can't be a degree 2 function because if I check the sum of the orders of the x-intercepts, this is order 3 and this x-intercept is order 1, so it has to be at least degree 4. So that's one instance where just doing 1 more than number of turning points is going to get you the wrong answer. You also have to check the sum of the orders of the x-intercepts. Let's check it the other way. Okay, this function, what if I were to only look at the sum of the orders of the x-intercepts? Well, this one's order 2, this one's order 1. The sum of those is 3. But the least possible degree of this is not 3. It's way more than 3. How do I know that? Well, because I know it also has to be at least one more than number of turning points. And how many turning points are there? I see 1, 2, 3, 4, 5, 6. That tells me it has to be at least degree 7. So my point of showing you those two things is just to prove to you that we have to check both of these in order to figure out the least possible degree. Okay, let's do a little bit of graphing. This is the main example I want you to be good at from this lesson. If you can do this example, then you can clearly demonstrate everything I need you to from this lesson. I'm going to give you the factor form equation, and you're going to do a rough sketch of its graph. And we're going to fill out a table of properties that are going to help us with the graph. So I'm always going to ask you for these questions. So I'm going to give you an equation in factored form and then ask you to tell me about the degree, leading coefficient, and behavior, x-intercepts, y-intercept, and sketch a graph. So how are we going to do that? I'll talk to you about it as we go through. So if I want to figure out the degree of this function, if it was in standard form, that'd be fine. That'd be easy to do. We just look at the highest degree term and look at the exponent on it. But this is in factored form. So what we'd be looking for, we'd be looking for what would the exponent on the highest degree term be? And the highest degree term would be the one that's a product of all of the x's. So if we were to multiply this x by that x, and then that product by that x, I would know that would be my highest degree term. And that's what this tells me here. So the exponent on the x when all factors of x are multiplied together. That's what we just talked about. If we were to multiply this out into standard form, one of my terms would be a product of that x with that x with that x. That would be my highest degree term. And x times x times x, three factors being multiplied with the same base, we'd keep the base, add the exponents, it would become x cubed. Therefore, it's degree 3. Another way to find it, which is probably easier and probably what you'll do, just add the exponents on the factors that involve an x. Order 1, order 1, order 1. Add the orders. It's 3. And that's what that tells you here. Add the exponents on the factors that include an x. Now, if we want the leading coefficient, what we have to do is we have to multiply the coefficients of all the x terms. So the coefficient, well, this one's easy. The coefficient of these x's are all 1. So if I want the leading coefficient, I would just do 1 times 1 times 1. We're just interested in that highest degree term I was talking to you about. What would be its coefficient? So multiply the coefficients of all those x's, 1 times 1 times 1. That is 1. So leading coefficient is 1. So I've got a positive leading coefficient, odd degree. I know that's going to go from Q3 to Q1. We learned that in the first two lessons. X-intercepts. Well, what would make each of these factors become 0? Because x-intercepts have y values of 0. So how can this function become 0? The whole function would become 0 if any of the factors were 0. So if x was 1, this factor would become 0. If x was negative 2, that factor would become 0. And if x was negative 3, that factor would become 0. And if any of those factors were 0, the whole product would be 0, meaning it's an x-intercept. So my x-intercepts are at 1, negative 2, and negative 3. And I always want you to write the orders of the x-intercepts beside them as well. These ones were all order 1. Y-intercept. How do we find the y-intercept? Well, the y-intercept, I know any point on the y-axis has an x value of 0. So just sub in 0 for x. And let's evaluate it. So f at 0. I'd have 0 minus 1 times 0 plus 2 times 0 plus 3. So that's negative 1 times 2 times 3. That's negative 6. So my y-intercept is the point 0, negative 6. So with all of this information, we can draw a pretty accurate graph. Let's plot all of our x-intercepts and y-intercept. So negative 2, 0. Negative 3, 0, and 1, 0. And the y-intercept is at 0, negative 6. And I know the function starts down here in quadrant 3, finishes up here in quadrant 1. And based on the order of the x-intercepts, I know the function is going to go straight through each of the x-intercepts. So this is going to be just a rough sketch. It's not going to be completely accurate, but the function would look something like this. Starts in Q3, goes straight through each of the x-intercepts. It's going to pass through all of the points I have, so make sure I pass through the y-intercept, straight through this x-intercept as well. Arrows on both ends to show that this is a continuous function, and there's a rough sketch of the function. On the next slide, I have Desmos's version, the perfect version of the function, and notice what we have looks very close to that. I mean, I don't have these turning points in the exact right spot, and you won't learn how to figure out where to put those until you take the calculus course. But for now, all I'm interested in is, do you have the x-intercepts in the right spot? Do you have the shapes at these x-intercepts correctly? Do you have the correct y-intercept? And do you have the correct end behavior, starting and ending in the right quadrants? So let's try 3 more. So the degree, just add the exponents on the factors that have an x. So 2 plus 1 is 3, another degree 3. The leading coefficient, I have to multiply all the coefficients of the x's, and I also have to multiply that by this factor of -2 as well. So the leading coefficient, I would do -2 times this 1, and there's actually 2 of them, so times 1 squared. I know when it's a 1 it doesn't matter, but if it wasn't a 1, it would be very important to be squaring it. And this coefficient is a 1 as well, and it has an exponent of 1 on it. So -2 times 1 squared times 1 is -2. So -2 is my leading coefficient. End behavior, negative leading coefficient, odd degree. That would tell me it goes from quadrant 2 to 4. The x-intercepts, I look at the x values that would make the factors become 0. So this factor tells me there's an x-intercept at 1, and this factor tells me there's an x-intercept at -2. And then at 1, the x-intercept is order 2 because of the exponent on that factor. And at -2, the x-intercept is order 1. The y-intercept, I'd have to plug in 0 for x and solve for y, so I need g at 0. So just plug in 0 for that x and that x. I'd have -2 times -1 squared times 2. -2, -1 squared times 2. So that'd be -2 times 1 times 2, that's -4. So my y-intercept is at 0, -4. So let's plot the x-intercepts and the y-intercept. Make sure I have the proper end behavior, so starting up here in quadrant 2, finishing down here in quadrant 4. And at the x-intercept of -2, it's going to go straight through because it's order 1. But at the x-intercept of 1, it needs to bounce off. It needs to make that parabola shape because that's order 2. So here's what this function would look like, approximately. Make sure I bounce off, form the parabola at that x-intercept, right? X-intercepts of even order, the function is not going to change signs around that x-intercept. It's going to bounce off. Odd order, like order 1, it's going to go through and change signs. So let's make sure that this looks like a good representation by comparing it to Desmos's graph. And there we have it. What we have looks pretty good. Part C, this one, degree. Well, the sum of the exponents on the factors that have an x are 3 plus 1, which is 4. This is degree 4. Leading coefficient, I'd have to multiply this -1 by this 2, right? I'm multiplying the coefficients of all the x's, so this 2, and keep in mind there's 3 of these factors, so there's actually 3 of those 2, so I'd have to multiply it by 2 cubed, and by that 1. -1 times 2 cubed times 1, that's -8. So I have a negative leading coefficient, even degree. That tells me it's going to go from Q3 to Q4. The x-intercepts are the x values that make this become 0. So if I can make that factor become 0, the whole product will be 0, meaning it's an x-intercept. And same logic for that one. So what x value makes this factor become 0? Sometimes people get tripped up on that. Well, what makes 2x plus 1 become 0? If it helps, make yourself a little equation and solve it. And you'll see the x-intercept is actually at -1/2. So my x-intercept is at -1/2. And this one's easier. An x value of 3 would make that become 0. So 3. And the orders, well, at -1/2, it's order 3. And at 3, it is order 1. Y-intercept. Let's plug in 0 for x into the function and solve for y. So let's calculate h at 0. If I did that, don't forget about this -1. If I plugged in 0 for this x, I'd just be left with 2 times 0 plus 1 cubed. So that's just 1 cubed, which is just 1. And 0 minus 3 is -3. This would give me 3. So 0, 3 is a y-intercept. So let's plot what we have. The y-intercept at 3. Okay, that's really low here. It's about right there. My x-intercept's at -0.5 and 3. And I know it's going to go from Q3 to Q4. Okay, it starts here, finishes here. And at the -0.5, it's going to look like a degree 3 power function. It's going to make an S shape. So here we go. Let me do my best here. So it's going to make this S shape through. I don't know how high it's going to go here. I'm going to guess right about there. And then it's going to come back down and go straight through this x-intercept here. It's going to look like a degree 1 power function. Go straight through. So they're both odd order. So notice the function does change signs at each of the x-intercepts. But notice the S shape at the x-intercept of -0.5. And notice straight through the x-intercept of 3. Let's compare that to Desmos's graph. Oh, okay, the turning point's a lot higher, but we have the correct x-intercepts with the correct shapes and the correct end behavior. Last one. Oh, this one's in standard form. If we want to graph this, we've got to get it into factored form. And I said we'll learn that next unit, but we actually don't need anything beyond grade 10 skills to be able to put this into factored form. Look at all 3 terms. They all have an x. In fact, they all have at least 2, so we could common factor out an x squared. So common factor out an x squared from all 3 terms. And then this second factor that's in brackets is a quadratic that we could factor by finding the correct product and sum. The numbers that multiply to 3 and add to -4 are -3 and -1. There, that's in fully factored form. Degree, well, I could tell that from standard form, it's degree 4, or I could add the exponents on the factors that have an x, 2 plus 1 plus 1, 4. Leading coefficient, well, I can tell here it's 1, but I could also figure that out by multiplying the coefficients of the x's. 1 times 1 times 1, that's 1. End behavior, positive leading coefficient, even degree, that means from 2 to 1. X-intercepts, well, I can't tell from standard form, but from factored form, I can see 3, 1, and what would make this factor become 0? What could I plug in for x to make that become 0? Well, 0. So 0, 1, and 3 are the x-intercepts. At 0, it's order 2. The other ones are order 1. And the y-intercept, hey, actually, I already have it. This point right here, that's on the y-axis. So point 0, 0 is also the y-intercept. All right, let's plot what we have and graph it. So straight through those 2 x-intercepts, but bounce off the x-intercept at 0, 0. So I need to bounce off this one, but go straight through that one, and straight through that one. So that's roughly what it should look like. Let's compare it to Desmos. And there we have it. The last thing we need to do is kind of go backwards from what we did for the last example. Last example, I gave you the equation in factored form. You came up with the graph. Let's do the opposite. I'll give you the graph. You come up with the equation in factored form. So we're going to follow these 4 steps, and I'll reference them as we go through. So here we go. Here is the graph of a polynomial function. First thing we want to look at, let's look at the x-intercepts. I see an x-intercept at -2 and at 3. So I could figure out what factors would create those x-intercepts. And I can tell based on the shape at those x-intercepts that they're both order 2. So I would know to put an exponent of 2 on both of those factors. So let me start by doing this. I'll call this function p at x for polynomial function. I know a factor of x plus 2 would create that x-intercept with an exponent of 2 on it because of this parabolic shape at that x-intercept. And a factor of x minus 3 would create this x-intercept. And I have to put an exponent of 2 on it because I can tell it's order 2 as well. But this is not the correct equation of this polynomial function. There are an infinite number of polynomial functions that have those x-intercepts of that order. Let me show you in Desmos what I'm talking about. So here's graphed what I've written here. Notice, I mean, if you were to think of a number being out front, right now we have a 1. So right here, I have a k in front. I have the k set to 1. Here's what it looks like. This function does not go through this 0.24 that this graph does. I need this function to go through this point. So I need to vertically stretch or compress this until it goes through that point. There will be only one graph with those x-intercepts that goes through that point. So I need to manipulate this k value to figure out what can I make k to make this go through that point. And it looks like there, 0.25. 0.25 is what's going to work. How am I going to figure that out? Well, we know this 0.24, this xy point, has to be on the graph of the function. And I know there's some parameter here that'll make it go through that point. I'll call that parameter k. You can call it whatever you want. I decided to call it k. What I need to do is substitute in this 0.24 for x and y, and then solve for what value of k makes that true. So the value of y is 4, so replace p at x, which means the y value, with 4. We'll leave our unknown k, but then replace each of the x's with 2. And now we just solve for k. So 4 equals k. Make sure you follow BEDMAS. So do in brackets first. 4 squared, -1 squared. So I have 4 equals k times 16. Now I'm showing a ton of steps here. You don't have to show all of this. K times 16 times 1, well, that's 16k. Divide both sides by 16. I get k equals 4 over 16, which is a quarter. That 0.25 that we saw works. So I could write the correct equation of that function by putting this k value of a quarter in front of the factors. So a quarter, x plus 2 squared, x minus 3 squared. So that's it. That's how we do it. Not too bad. Part B, I don't actually give you the graph, I just give you some information about it. It says find the equation of a polynomial function that is degree 4 with zeros, -1, order 3, and 1. So that must be order 1 if it's degree 4, right? The orders have to add up to the degree. So order 3, this x-intercept must be order 1. And there's a y-intercept of -2. Keep in mind that y-intercept is a point. It's the point 0, -2. So we have an xy point, and we have the x-intercepts. So let me write the equation of the family of functions that have those x-intercepts first. That means put that k parameter and then the factors that create the x-intercepts. So the x-intercepts are -1. I know a factor of x plus 1 would create that x-intercept, and it's order 3, so put a 3. And it also has an x-intercept at 1. This factor would create that x-intercept. And since this is a degree 4 function, I know that this one must be order 1. So I don't have to put that 1 there. And now let's solve for the equation that passes through this y-intercept, 0, -2. So plug -2 in for y, and plug 0 in for x. And then we can solve for k. So I have 1 cubed, that's just 1, times -1 is -1. So k times 1 times -1, that's -1k. Divide both sides by -1, and I get k equals 2. So my polynomial equation, p at x equals 2 times x plus 1 cubed times x minus 1. And there's my final answer. All right, for this section, make sure you try out the practice questions.